All right. Is everybody able to see my screen?
Yes, sir.
Yes, it is visible.
Cool. So I'm just gonna. So the flow of my sharing today, since we have a wide range of audience, I believe from junior collegiate students to people who are probably already quite well versed in orbital mechanics. So just to keep the bases all covered, I will start with some very simple concepts, and then we'll move on ahead into what are some of the present day research interests that people have in astrodynamics. In particular, what are some of the research works that my team has done in DSO, and what are some of the works that my current team in Stanford are also doing. And actually, both sides are equally, there's quite a lot of common interest in both that sense. So I'm just going to maximize my screen. Is the screen maximized for everyone? Is anybody seeing any glitches?
Yeah,
No,
it's
it is
all fine.
perfect.
Yeah.
Perfect.
Perfect.
Okay,
Yeah.
so let's start. So this is orbital mechanics for space mission design. So we're going to start a little bit simple first before we move on into the more detailed oriented and some of the more relevant modern literature. And so before we start, maybe let's keep it active. Maybe I'll ask a few questions. Let's see, who do we have in the audience? Can we ask Mohit Kumar, what do you think orbits are all about? Okay, I
See,
guess.
just like Samuel, I would like to encourage everyone, just like what he's doing with asking questions. You please come up and you can answer whatever you feel. We are there to correct you. So
Yeah,
whatever you have the
So
perception of.
can I say?
yeah, go ahead. Go ahead.
Uh, Actually, it means a curved path of an object that is revolving around the planet. That means
Yeah, exactly. So a lot of us, so anyway, now and then, just to keep the session interactive and just so I can put a name to your faces and try to understand or know some of you. Also, I think I'll ask a few questions now and then. And so orbits, a lot of people think orbits are all about space. It's about things moving in space, and that's fine, that's true. But I want to change the way we think also, and orbits are also a bit about time. Why? Because an orbit is basically a trajectory, ideally in a two-body sense, that goes along a goes along a path where it's energy invariant, right? So you're free falling in space because you are traveling along the path where there is no change in your total mechanical energy. And so because of that, that also constrains the time that it takes for you to revolve around the planet. So Kepler's law says that your periods are proportional to, or rather proportional to, the power of 3 over 2 of your orbital radius for a circular orbit. And so a lot of these orbit designs, you have to consider not just the space, but the time. How often do you want to revisit a particular location, and so on and so forth. So it's just to prime the way we think a little bit about space mission design. It's a 4D problem, right? And just want to give you guys a bit of an introduction. So I'm relatively new myself to the space industry. I just graduated from my bachelor's in 2018. I didn't even know that we had a space program in Singapore. And these are some of what we've done. So GPS is definitely not by us, but I mean, it's just a very common, Barani, you have a question?
No, sir.
Oh, okay, because I saw the hand have existing comms satellites that we have bought, not built, but the ones at the bottom are what we're actually starting to build since 2015. right? So Helios 1 was our first optical imaging satellite that was built in Singapore. And Singapore was always very small. We're a tiny island. We have 2 satellite research centers, public ones. One is by the National University of Singapore, and one is by the Nanyang Technological University. And DSO, it stands for Defense Science Organization, but we basically do anything under the sun with regards to space, aerospace, electronics, you name it, we've got it. So Helios 1 was an optical imaging satellite, and Helios 2 was a radar imaging satellite. So for people who just not too familiar with the idea of radar imaging, you can Google synthetic aperture radar, and the key idea is that you can send pulses, radar pulses, out in the range and the azimuth direction, and the scatter, the information that you get back into your satellite can tell you information about the brightness of each pixel on the screen. So that's pretty cool. It's very different from optical imaging, where you just take a passively lit photo that was illuminated by the sun. In a radar image, you actually illuminate, you are the flash, and you illuminate the whole area. And then we also have our first formation flying program, the 3 birds, Lumilights 1, 2, and 3. These 3 were the projects I was actively working on, where we were trying to do satellite navigation, especially relative satellite navigation, which is one of the core pillars in formation flying, right? So for formation flying, we want to make sure we have guidance, we want to have navigation, and we want to have control. So relative astrodynamics comes into the formation part, into the guidance part. We'll use GPS or differential GPS or RTK for the navigation part, and we use and for control, we can still rely on very traditional linear quadratic regulator kind of control to do it. Or we can even find exact optimal impulsive solutions for it. So these are just some of the satellites around us in Singapore, just to give you guys an introduction. And I think most of the audience are from India. So just like a kind of a fun backstory, back then, I think like 15 years ago, we actually didn't really have a very strong space team. So we sent a team of DSO scientists to work with ISRO. We sent them all the way up in the mountains, and we were actually learning from the Indian scientists. And even today also, we work a lot with ISRO to discuss things like launch schedules. We even have scientist exchanges and all that. It's actually pretty fun. And of course, there are also satellites very far away from us. So James Webb has cleared, I think, one of the critical design review. No, I think it was a launch readiness review, and it's undergoing its final prep. Rosetta was meant to sample asteroids, and Juno was shot out all the way to Jupiter to explore the planet. And some of the pictures that Juno has taken are quite incredible. So how do satellites actually fly around Earth? The common way, I think a lot of us are taught, right, is the Newton's cannonball paradigm. So you can just imagine I'm going to throw a tennis ball and it's just going to land on the ground. But what if I stand high enough and throw a tennis ball far enough such that the radius, or rather velocity vector, of the tennis ball is always directed such that it is fast enough to miss the curvature of the Earth. So ideally, if I throw a tennis ball in the second picture over here, or the third picture, by the two-body kind of a mechanics, that tennis ball will probably like come from the back and like hit me on the head in like another 95 minutes or so, right? Of course, that doesn't happen, because in reality, there are perturbations and drag and all forms of things that perturb your satellite orbits. But that's a bit more towards the slightly advanced side. So we're going to go ahead into the basics. So for some of our younger students out there, there are quite a few projects, open source apps that you can just try to get a simulation on Newton's cannon. So I'm going to be breaking the basic part of orbit design into shapes and sizes versus the orientation. Okay, so a lot of textbooks give you this very dry here are the 6 orbit elements. I'm sure a lot of us know what the 6 orbit elements are, right? And like, yeah, just memorize them because that solves for your 6 degrees of freedom. And but I want to give us a more intuitive idea on why the orbits are shaped like that, okay? And when we think of the shape of an orbit, and so we're going to confine ourselves in this discussion mostly to closed orbits. So orbits where they don't escape the gravity well of the planet, right? And so generally orbit shapes are classified as conic sections. And a conic section is, let me see if I can just skip to the next slide. No, okay, I don't think I have that diagram here. But a conic section is basically just a cross section of a cone. So imagine if I have a cross section of a road cone, like one of those road cones you see on the streets, right? And I just take a cut of it. At a certain angle, if I cut it perpendicular to the plane that's normal to the axis of the cone, I get a circle. If I cut it in an oblique shape, I kind of get an ellipse. And at certain angles, when I cut it at the same slope angle of the cone, I get a parabola. Anything steeper than that, I get a hyperbola. So that's just a kind of an intuitive way to think about it. But I'm going to explain what a semi-major axis and what an eccentricity is. So semi-major axes is basically a term not just to describe orbits, but ellipses or parabolas in general. So for an ellipse, a semi-major axis is half, so that half refers to the semi, right? Half of the longest length of the ellipse. So for a pure circle, the radius is constant everywhere, but for an ellipse, I have a long edge and I have a short edge. So semi-major axis refers to half of the distance of the long edge. And the eccentricity actually defines the shape, and I'm going to show you why, right? So these are orbits that have the same semi-major axis, for example, but different eccentricities. And these are orbits that have the same eccentricity, which means the same shape, but different semi-major axis. So you can just see like they are the same shape, just scaling up in space. But what exactly is it, and how do we actually relate it? So I'm going to deviate a bit from the typical astrodynamics textbooks or space mission analysis and design, where they give you the 6 elements. And let's go a bit into the math, the origin of why conic sections were. I have a question here. Most of the orbits are elliptical due to error in projectile or pre-plans. So an ellipse, so that's a very good question. Orbits by themselves are not necessarily circular, right? So when an orbit is in an ellipse, that is the path that it takes where the total mechanical energy is conserved. So in an ideal universe where there's just nothing but, let's say I have a single planet over here, right? And I don't perturb my satellite. I just let it do its thing. I just let it fly. It will follow any one of these 4 possible trajectories. It doesn't have to be a circle. And of course, perturbations are everywhere, so these shapes are not going to be ideal, right? I think I have a question from go ahead, Manit.
What are the chances for these to happen? Like, what are the chances for circle, that oval one and the other 2 parabolas?
Okay, that's a very good question. So that really depends on what is your initial conditions. So when I launch a satellite into space, an orbit, right, can basically be defined by your initial radius vector, so your xyz in space, and your velocity vector, your xyz rate in space. And actually just knowing what is the radius and the velocity at that instant in time allows you to propagate the entire orbit. So if I have, let's say, let me do a simple. So I'm just going to bring attention over to my video instead of my slides. So if I have a satellite that's starting at the same radius vector, but with a very high velocity, I may end up going into an ellipse, But if I do not have sufficient velocity, right, I will probably just like end up hitting the ground. You see the motion? And for a one particular velocity value, I will be able to enter the circular orbit. So that's just kind of how it works. There's a whole there isn't a driving force for keeping orbits in those shapes in that sense. So, and in the interest of time, I'm just going to move on to the next part, which is to talk about how semi-major axes and the eccentricities all come together to talk about the orbit shapes. So I want us to think about three things when we look at the eccentricity of an orbit. So eccentricity is not only an orbital parameter, it's a constraint equation. And so this is beyond the realm of orbits. Now we're going into math, and we're going into the study of ellipses in general. So it could be an ellipse on, I don't know, let's say, what are some of the ellipses that we know in nature? Anybody have an idea? Natural occurring ellipses.
No, sir.
No? Okay. Well, anyway, we want to take a look at what a focal point is and a reference line. So I'm going to introduce two very alien terms here. Okay. And in math, in geometry, an eccentricity is defined as the ratio between PF and PD. So I'm going to explain what P is, what F is, and what D is. So first, F is a particular focal point, right? I haven't actually said what this focal point is with respect to our solar system, but you can make a rough guess. D is an imaginary line which we will use as a reference, and which actually with these 2 points, with this line and this point, and a defined eccentricity, we can actually find the locus of all the points that satisfy this constraint equation. So that's a lot to take in. I'm just going to go through an example, okay? So let's say my eccentricity right now, again, purely geometrical, no space, no orbital mechanics. I'm going to set my eccentricity to a particular value, okay? And I want to trace out all the particular points P that correspond to this ratio. Okay, so that's what locus of points mean. Okay, so I'm going to trace out all the possible values of P, and I'm going to show you a bit of a magic over there, yeah? So let's start with the eccentricity of a parabola, and it happens to be 1, and let's see why. Okay, so again, eccentricity is a constraint equation. I have a particular focal point which I begin with, that's F, and I'm going to come up with an imaginary line called the directrix, D, and I force the eccentricity constraint equation to be equal to 1. So let's see what this does. Right now, what I've done is I've just created equidistant vertical axes in the x-axis and equidistant radial axis along the polar radius axis. And I'm going to draw an imaginary directrix line here. So can anybody, so before I actually start animating the diagram, I will draw the first point, right? So let's look at this first point over here. This is one particular point P, right? Where the ratio between PF to the perpendicular distance to PD is actually 1. Can everybody see that?
Yes, sir.
Yeah, so this is like really boring, right? It's just one point, it's a straight line. What am I going to do with this? Okay, why not we find the next point which satisfies this, right? And let's find a point in space. Let's find another set of points P where my ratio is still 1:1. So look at these 2 points. These are 3 units in radius away from the focal point and 3 units in the horizontal axis towards the directrix. So 3:3 is actually a ratio of 1. And we can find another set of points where it's 4:4, right? Let's count this again. There's 4 units in a radial direction, 4 units in a horizontal direction, and there's 5 units, and there's 6 units. And if you actually trace out all of these lines, right, this constraint equation, just by setting the eccentricity value to be equal to 1, gives us the shape of a parabola in a mathematical sense. So I mean mathematical sense in that I haven't actually considered gravity, some of Earth's forces. So these are just shapes. And I can get this shape purely just by setting one constraint equation, having one focal point, and one directrix. And for some of the more observant students, you will probably make the right guess that yes, indeed, the focal point for an Earth orbit would probably be D. Anybody want to make a guess? Let's have Nafisa. Nafisa, do you want to make a guess? What would F be for a real life astrodynamics scenario?
I don't have idea, sir.
So F would actually be, so let's say if you were flying a satellite around the Earth, F would actually be the center of the Earth, right? So a satellite doesn't have to be a man-made thing, right? Our Earth, our planet is also a satellite about the sun. So imagine if one day we decide to give the Earth a really, really strong push. The Earth could just leave the solar system in a trajectory too, and that's fine, right? So that's basically how the eccentricity equation defines the shape of a parabola. And so we're going to look at eccentricity as an ellipse right now. So this time we're going to go through the same thing, but we're going to set the constraint equation to 0.5, right? 0.5 meaning that the ratio between PF, where remember that P is a variable point, it's a locus of all the points that satisfy this constraint equation. Now the ratio is 1:2 or half, right? Same thing, I'm just going to draw a bunch of concentric circles to just show the equidistant points along the radial axis. And I'm just going to draw the first point over here. Now this distance is 2:4, which corresponds to half. And I can continue drawing. This set of points is 3:6, right? If you count 3 in the vertical direction, 6 in the horizontal direction. Now that's also a ratio of half. And if I continue drawing these sets of points, notice that I have actually defined, okay, so I'm just going to give you some time to check back. Look at the last point here. This last point has a distance of 12 units to the directrix and 6 units to the focal point. So that's a ratio again of 1:2. And notice that the only thing I didn't actually change the constraint equation structure. All I just did was change the value of the constraint equation, right? And this completely changed the trajectory of where this shape would be. So this is an ellipse, and in particular, it's an ellipse with an eccentricity of 0.5. And so these are very useful for us in defining what the shape of an orbit is. In fact, actually, there's a very rigorous proof, which is not trivial. In fact, it may seem like, oh, two-body physics is like solved 200 years ago, but there is a non-trivial proof that shows that Newton's law of gravitation eventually, if you include the conservation of energy into its equation, gives you the equation of motion of a conic section. Again, it may not be a circle, it may not be an ellipse, it could be a parabola too, right? Depending on what the value of the eccentricity E is. Okay, so I'm just gonna stop here for 30 seconds. Okay, yes, what was the DD line again in the previous image? Good question. So the DD line is just an imaginary line. It's called a directrix. So in the astrodynamics term, the directrix doesn't play, besides defining the shape of an orbit, the directrix doesn't play a very crucial role in the sense that it doesn't actually exist. Like there isn't a line that's really just floating around in space, right? Dev, you have a question?
Yes. Hi, Sam. So I just want to know that what is the main factor that distinguishes between any two orbits? Like if we have the low Earth orbit that reaches up to 2,000 kilometers from the ground, and we have the geosynchronous orbit that reaches till 20,000 kilometers. So what's the main difference between these two particular orbits, and another than the altitude that they sync each other?
That's a very good question. So so I haven't actually talked about this yet, right? But physical parameters in an orbit are all interrelated and all coupled. And what I mean by this is that although you have changed from low Earth orbit altitudes, let's say 1,000 kilometers, up to a geostationary, which is typically about 36,000 kilometers, while your altitude has changed, if you actually formulate the orbital mechanics from, if you look at Kepler's laws, your altitude, which is equivalent to, or rather which scales with your orbital radius, would change things like your period, how frequently you fly around the Earth, your velocity also. So when you change altitude, you change a lot of many other parameters of the orbit. So I won't say that there's a distinct class between like LEO and GEO. That's more of just for policy and planning purposes, right? In physical reality, it's a continuous distribution, it's a continuous flow. If I raise the orbit higher, my period gets, I take a longer period of time to orbit the Earth once. And for a geostationary, as you've mentioned, there is one particular solution for an altitude where I would orbit around the Earth exactly in 1 day. And so I would just kind of follow the rotation of the Earth if I was an equatorial orbit, or if I was an inclined orbit, then I would make some kind of a figure of 8 shape around the Earth. So that part's pretty interesting, and that comes in the more advanced orbit design methodologies. All right. So we're going to stick to orbits that are bounded, which means that they don't have sufficient energy to escape the gravity well of the Earth, because parabolic and hyperbolic orbits are beyond the scope of this presentation. Okay. So we've talked about how we size orbits and how we shape them. Now let's talk a bit about the orientation. So with the I think I have another question. For docking, whether both the objects need to be at the same eccentricity? That's a good question. The answer typically in practice, it's yes. But if you actually draw it out, you don't need to be in the same eccentricity, right? You can always, so let me see if I can draw, let's annotate. Oh, let's try this. This is fun. Draw. Okay. All right. Can everybody see my writing? I just scribble a bunch of white lines.
Yes,
sir.
Yeah, it's there.
Okay, yeah. So let's say I have the Earth over here. I have an elliptical orbit. Of course, I can always solve for a particular point where I have a second elliptical orbit that reaches, that kind of intersects, right? But in practice, this is not feasible. And why this is not feasible is that because if you look in the direction, let's say right now you are looking in the inertial frame of the Earth and the orbit and everything, and it looks nice, like, oh, there's an intersection point here. If you actually go into the local reference frame of the satellite, let's say you are now sitting on the satellite right now and you're looking at it, from your perspective, what you will notice the other satellite in the other orbit doing when it has a different eccentricity is that it's just going up and down, up and down, up and down, up and down from your perspective. So it makes it very difficult to chase and capture that satellite, right? Because in that moment, this guy is going to be going here, and while you are, I don't know, you could be going in some other direction. And so there's going to be some kind of a vertical motion, which makes docking very, very difficult if your eccentricities are not the same. So beyond the eccentricities also, not just the eccentricities have to be the same, the argument of periapsis has to be the same also, right? Because even if you have the same eccentricity, you want to make sure that the orientations of the orbits are aligned, right? So you want to make sure that both orbits are aligned, so you kind of follow the same trajectory and it makes it easier. So there are catch-up and docking rendezvous maneuvers that we can take also. And actually, it just kind of leads into the next part of the sharing also, which is, how do I erase all of this? This doesn't, let's see, eraser. Okay, there we go. All right. So that kind of leads into the next part of the sharing, which is the orientation of the orbit, right? So we've talked about the shape, eccentricity, and semi-major axis. So right now we want to talk about how we orient the orbit in space. This is a diagram that you'll probably very commonly see in most astrodynamics textbook. It tells you, oh, okay, let me just use a piece of plane. Okay, so like for example, this is my orbit, right? And then you can tilt it, incline it, and then you can rotate it about the local z-axis, which is your right angle of ascending node, or you can even do by the argument of periapsis, which kind of rotates it about the local orbital plane. I'm just going to give you guys a very visual understanding of this in the next few slides. But before we do that, I want to introduce a satellite ground track. So the idea of a ground track is the shape that your orbit projects onto the Earth's surface. And so we know the Earth is a 3D sphere. What happens if we actually project a circle, right, a circular trajectory around Earth onto a round object? So let's look at this tin can example. I like this tin can example. And I use this a lot when I give this lecture to the young defense scientists back in DSO, right? If I project and trace out the circular orbit around the can's body, and then I proceed to cut up the can and I flatten out the aluminum pane of the can, you'll notice that it gets kind of like a sinusoidal shape, and that's because this is we call it a stereographic projection on it from a round surface, and we want to project and plaster it onto a flat 2D map, and you'll see this sine wave over here, right? And we see this with the Earth too. And this sine wave that you see is kind of moving slowly with the Earth, because while the satellite is spinning around the Earth, your Earth is actually rotating underneath it. So if you were an astronaut and you flew out into like the wide open space and you're looking at the orbit, the Earth is just kind of like spinning and doing its thing. Let's see if I got an Earth over here. So the Earth is just kind of like spinning and doing its thing. And then your orbit is the orbital orientation is not going to change ideally in a two-body sense while the thing is rotating. So because of that, somebody that's resting on the surface of the Earth that's rotating, from his perspective, the first orbit will follow a trajectory shown in red, but the second orbit will follow a trajectory that's slightly pushed, because the Earth has rotated a few, maybe tens of degrees across the period of time by the time the second orbit gets there, right? So this is the notion of a satellite ground track, and this is really, really important when we are designing Earth-based space missions, right? So keeping ground tracks in mind, let's go back and revisit what the 4 orientation parameters are. The first is the inclination, which we're going to talk about. Then the argument of perigee, or periapsis if you don't want to specify the planet. Right ascension of ascending node, and the true anomaly. All right, so let's look at the orbit inclination. Let's introduce a series of satellites with different inclination angles with all other orbit elements kept constant. So this is an inclination of 0 degrees, and the inclination refers to the tilt of the orbit plane with respect to the equatorial plane about the line of nodes, right? So you can think of the line of nodes as just some vector that's pointing out of the Earth, that's towards some very far distant star that rotates very, very, very slowly with respect to us on Earth, such that we can treat it almost like as a constant position far away. So it's just kind of like tilting. So if I have an orbit plane here and the line of nodes over here is kind of like tilting about this, where this axis of tilt lies on the equatorial plane. So let's add 2 orbits with inclinations of 15 degrees and 30 degrees, just to give you an example, just to show you what I mean by that. And we can actually just keep adding more. You can add so many orbits spaced 15 degrees apart so these are different orbits with different inclination angles, right? The one that's kind of flat, horizontal, that's called an equatorial orbit. And the one that's inclined all the way up to 90 degrees, that's called a polar orbit. And this looks, okay, yeah, this is fancy, this thing flies around in space, but what does it actually mean for us on Earth, right? Because remember, the Earth is a rotating object. So what we actually study in mission design is how the inclination can affect where we want to reach in latitude. And what I mean by this is, if you notice, the Earth is spinning around here, and let's look at the inclination that's tilted at 30 degrees, right? So notice that if I tilt my inclination at 30 degrees, right, I am only bound to revisit at the very highest end a latitude of 30 degrees, around 30 degrees. It's not going to be exact because I'm going to have some kind of a sensor cone. I'll be able to tilt my satellite in an oblique way. But basically, the idea of the inclination is that it allows us to reach higher in latitude, right? And let me erase this. Okay. Done. And let's look at what it looks like on the ground track. So at a 0 degree inclination, I'm just flying around the Earth's belt. This is satellite 1. If I increase my inclination, this is 15 degrees, 30 degrees, and notice that the amplitude of the sine wave, right, peaks also at about 15 degrees and 30 degrees. And if I add it all the way up to 90 degrees, you get this like really funky pattern where the satellite just traverses all the way to the North Pole. So does anybody want to make a guess which line belongs to the inclination of 90 degrees?
The straight line?
Yeah, which straight line? There's like two.
The one perpendicular to Africa.
Yeah, you're right. And does anybody want to make a guess why there are these like funky lines? So let's look at the bottom over here, right? Notice that the satellite trajectory makes like a really, really sharp turn here. Does anybody want to make a guess why?
The satellite's passing by the poles.
Yeah, exactly, right? And at the poles, right? So at the pole is the only place where north, south, east, and west are or rather at least east and west, maybe sometimes even north and south is undefined, right? Because you're at a spot where you are the north, and when you actually project an area of infinitesimally small space and you flatten it out, it makes the place look a lot bigger than it is. So which is why one grid of distance over here is very different from one grid of distance over here. So this makes it look like the satellite made a sudden right U-turn, but in actual fact, it's actually just going over a very small geographical location in space, right? Okay. So just to recap, the idea of inclination is just to get us to bring us to a higher place. And we're going to talk about next is the right ascension of the ascending node. So right ascension of the ascending node is essentially just a rotation about the Earth's local z-axis, or rather the Earth's inertial z-axis, right? So the Earth is kind of rotating about and doing its thing. And I'm going to rotate my orbit plane this time around the Earth. So think of the axis of rotation as the z-axis here. Let me just draw it out. Yep. So I'll just do a rotation about the Earth. And what I did was I added two 45-degree inclined orbits at 30-degree right angle of ascension node spacings. And if I keep doing that, let's say I'm just going to keep generating orbits until it covers like the whole 360 degrees of Earth. It has this like really, really funky shape. It kind of looks like a bagel. It just covers everything. And this is what a lot of, like if you look at some of those Starlink constellations, even the GPS constellations use very specifically defined right angle of ascending node spacing. So remember, so Dev, you have a question?
Yeah, I do have a question. So we all know about the escape velocity of the Earth atmosphere, that is the velocity required to leave from the Earth atmosphere. But is there also the escape velocity of an orbit for a satellite to change between any two particular orbit? the velocity required to change from one orbit to the another orbit?
Sorry, what's your question?
Yeah, so my question is there also the velocity that is required to change between one orbit to another orbit?
Yeah, exactly, there is.
Yeah.
In fact, if you go, let me just go to the end of, if I just bring, I have like 130 slides. This is like my go-to slide if I need to teach, right? So I have an entire deck of slides just showing you how to change velocities from one orbit. Can everybody see this? Dev, can you see this?
Yeah, I can see it. Yeah.
Yeah, so I have an entire deck of slides at the back just showing you all the algorithms for computing what is the change in velocity you need to move to different orbits in space. So typically people use the Hohmann transfer or the bi-elliptic transfer algorithm. And I'm not covering it so early on in my slides simply because it's a bit more of an advanced topic. Yeah, so yes, it is computable, and yes, usually in the case of an impulsive solution, by impulsive I mean like you can immediately apply a sudden change in your velocity vector, there is an optimal solution for what is the change in velocity, or equivalently the change in energy that you would need in order to change from one orbit to the other. Yeah. Okay, it's 2 questions. We can calculate the velocity from the difference in potential energy, right? It is easier to do it in a circular orbit because your velocity is constant. So if I think let's relate this a bit to the high school physics that we all learned. So in a high school physics sense, if you're fixed orbit that doesn't have perturbations has a fixed amount of total mechanical energy, and within that total mechanical energy you can calculate the velocity. But if your satellite trajectory is elliptical, right, because you have to conserve angular momentum, because total mechanical energy is conserved, at periods in time where your satellite is closer to the Earth, your velocity is actually higher, and at periods in time where the satellite is further away from the Earth, your velocity is actually lower. Right? So for a non-circular orbit, your velocity is always changing. And so then the velocity difference in calculating a change in trajectory not only depends on your energy, it also depends on your position in space as well. So there's an interesting effect about this called the Oberth effect, where you exploit differences in height. We call this the perigee and the apogee. You exploit differences in height to try to give you the best cost savings in terms of change in energy or change in delta V to change your orbit. So it's beyond the scope of this presentation, but if anybody's interested in, let's see, Chattervedula, if I accidentally butchered your name, please forgive me. Yeah, if anybody is interested in Chatter's question, Google Oberth effect. This is an interesting effect where you can exploit differences in velocity changes, even though the orbit has the same potential energy throughout, but it's because it's non-circular. All right, so I'm going to move to right ascension of ascending node, which I did. So we made this bagel over here, right? This is a very nice bagel, or donut, right? And all of these orbits are 45-degree inclined, but spaced 30 degrees apart in rand. And this is kind of just like what the whole constellation looks like. Let's take a look at what it actually looks like on the ground track, because when we are planning for space missions, we want to make sure that we can predict where, or rather we can propagate where the satellite will be over a particular spot on Earth, which is easier to do it on a 2D ground track map. So this is a single 45-degree inclined orbit, and you can tell it's 45 degrees because the amplitude right now, remember, inclination defines how far we can reach in latitude, right? It's plus minus 45 degrees. And we're just gonna keep adding, and you see that we make this like really nice, I like to call these like fishnets because they just look like fishnets. You have this nice fishnet pattern where you show this to like professors, or you show this to like investors, to your VC investors for your startup. I mean, like, yeah, this is global coverage. This is the orbits that we've designed to reach every single spot on the Earth. And this is really useful, especially if, let's say, you want to reach, so I'm going to bring in a bit of the space mission design philosophy here. So let's say your satellite can only reach a very specific radius. Let's say your antenna can only cover this spot, and this spot. So if I actually draw out all my coverages, right? If I draw out my coverages, for example, so they're all flying. So the circle represents the footprint of my antenna. How wide can I scan the Earth or send a comms link to the Earth, for example? So how space mission design actually relates to the orbital mechanics design would be like, for example, let's say you need to reach certain places, and you notice that in between here, these are gaps, right? Oh no, because your spacing wasn't tight enough. So as your satellites are moving, notice this big patches of white. Oh no, these guys, let's say this is Starlink, and you want to send comms signals down to poorly served areas in rural regions. And you notice that these are the outage zones. So you have to do something about it. You need to replan your orbit, respace your entire constellation such that you'll be able to cover everything. So again, just kind of relate some basic mission design concepts. And then last, we have the argument of, no, not last actually, we haven't talked about satellite position yet. So the last of the orbit orientations, you have the argument of periapsis. Actually, I should pause here. Before I actually move on to that, does anybody have questions about this? We have one. Whether the different possibilities for shadow passing over Earth. Different possibilities for shadow passing over Earth is due to the tilted axis of the Earth or tilted orbit of the moon around the Earth. I suppose you're referring to eclipses. Are you referring to eclipses? Yes, you are. Okay, yeah, I see it. Yeah. So the tilted axis of the Earth, axis of the Earth and the moon. So the Earth actually, I think it's like 23.4 degrees tilt from the, I think, what did they call it? The solar, I forgot what's the heliocliptic plane or something like that. Solar systems plane. It would be great if you could demonstrate something using Leo GPS as well. Yeah, I could just run thank you. I think Vishnu, you know about my open source softwares. Yeah, I can do a demonstration at the end. Let me just do a time check. I don't know how. It's like, okay, I'm taking way too long for this. Let me speed up a bit because I want to talk a little bit more about the advanced concepts, especially for some of the members of the audience that already know all of this. So I'm going to introduce argument of periapsis, and argument of periapsis is basically just the orientation. So previously what we did was we rotated the orbit about the z-axis, right, of the Earth. But now what we're doing is we're rotating the orbit about the z-axis of itself. So this is the z-axis of the orbit plane. So you can think from this slide, you can think of the z-axis as it's pointing out of the paper, right? And if I keep rotating, I get this really, really nice, I call this like a floral constellation. Some people call it a floral constellation or flower constellations. You do it in rotational steps until you get a bunch of different orbits. So actually in reality, so again, this makes sense. Okay, so I'm just going to point out, this makes sense because I started off with an elliptical orbit. So notice that this orbit is not circular. If I have a purely circular orbit and I rotate about the z-axis of itself, it doesn't matter. Can you guys see that? So if I have a purely circular orbit, let me just draw it out here. This is the Earth, this is the orbit, right? And I'm just kind of rotating about, it's like, I shouldn't be drawing two concentric circles, that's just confusing. So if it's purely circular and it just rotates about itself, it doesn't matter. It looks like it's the same, it hasn't actually changed. But if it's an elliptical orbit and it changes over time, right? Or rather it rotates over time, then it kind of forms this nice floral pattern over here. This is undesirable in a lot of orbit trajectory designs. And actually this was a focus of one of my research works in earlier this year. But before we dive into that, let's just look at how it looks like on a ground track. So we've got a bunch of satellites. So the argument of perigee isn't so much related to the ground track you can't really relate space mission design concepts with the argument of perigee, besides just the local vertical variations in height from satellites. So yeah, any differences that you see between the ground tracks here are solely because of the Earth's rotation. So remember that your sine wave is always moving, right? It's moving because the Earth underneath is rotating, but your orbit is not. So let's say by the time S1 over here reaches the same position where S2 is, it would have moved by this amount. So that's why the ground tracks are not exactly the same. And right, so what do you think the argument of periapsis is for a purely circular orbit? Okay, we've kind of talked about this. Okay, we're going to introduce a true anomaly. This is like the final thing that defines the position of your satellite, right? So we've looked at the shape. We've looked at the size. We've defined the shape based on that size. And then we've kind of like done the tilts, right? We've done the inclination tilts, periapsis tilts, and the right angle of ascension node tilts. These tilts are actually, so for people who are coming from like aerospace robotics backgrounds, these tilts are actually known as the 313 Euler angles. It's a bit similar. So Euler angles are like your yaw, pitch, and roll. So it's the same as taking an object, doing a yaw, pitch, and roll. In this case, for a 313 rotation, it's a roll, yaw, roll, right? And then it still gives you the same degrees of freedom you need to specify an object in 3 degrees of translational position and 3 degrees in rotational position. So true anomaly is just the position of where you are along the orbit. It's just the angle about the argument of periapsis, or rather the line. Sorry, not the argument. It's the angle about the line that passes the line of apsides, which is a line that connects the furthest point of the ellipse to the closest point of the ellipse. So typically it looks like this, and periapsis is here. So this is your periapsis. So people would measure this angle here. So this is called your true anomaly. Yeah, so okay, I am going to move on. I think I don't have time to finish this part of the video. Okay, let me just erase this. So these are very simple basics. So we don't necessarily need to pick these 6 elements. There are other 6 elements, linear, some non-linear combinations of the 6 elements also. There are equinoctial orbit elements to prevent singularities, especially in cases where your periapsis is like 90 degrees, 0 degrees, or if your eccentricity is 0, for example, and that makes certain things undefined, especially when you divide over 0. So we use like equinoctial orbit elements also. But for most scenarios, like the traditional 6 orbit elements work. I'm going to talk a bit about advanced orbit design methodologies for LEO, and this touches a bit about some of the recent research works that I've done in the earlier this year, and some of the future research work that I'm probably doing at Stanford's Space Rendezvous Lab in the next probably like 5 years of my life. So just from these very simple concepts, right? Oh, sorry, I have a question. What is line of apsides? So line of apsides is let me just draw that again. So line of apsides is the point between the furthest point on the ellipse to the closest point on the ellipse. So if you just draw a line between that, it connects. Basically, a line of apsides is the line where the major axis is. So semi-major axis is half that distance, major axis is the full distance. And that line, which is where my cursor, I'm not sure my cursor can be shown, is where the line of apsides is where that line is. What happens if a satellite is launched vertically and released at its design altitude? What happens if... So chances are, if it's just launched vertically without any horizontal motion, the only horizontal component to your velocity that you have is the horizontal component due to Earth's rotation. And that is not enough to keep you in orbit. So if you just launch vertically and release it, you're just going to drop back down with some horizontal velocity component. But the Earth is also rotating, so that horizontal velocity component also kind of moves with you. You're just going to fall back down, which is why, like, if you notice, most launches, they just go up, and they immediately, once they reach a high enough point where atmospheric drag is not great, they immediately do a 90-degree turn and start accelerating in a horizontal direction. Okay, let's move on to advanced orbit. So this part of the talk will be a little bit more recent. And there's been a lot of interest. If you notice, a lot of startups, Capella Space, ISI, even some of our works with Nanyang Technological University and National University of Singapore, we designed a lot of orbits using frozen repeat ground track orbits. So simple concepts like what we've talked on in the previous slides, like all your 6 basic elements, how do we actually optimize them? How do we optimize them for revisit? So what is a frozen repeat ground track? So a frozen repeat ground track is basically so remember in the previous slides, I showed you guys like, oh, this is a ground track. This looks really nice, really pretty. A frozen repeat ground track is a ground track that basically repeats itself after a specific amount of time, a designed amount of time. And a lot of space missions have used this because they need to look at the same place from the same point of view periodically. Either that or it makes it easy for them to automate ground services. For example, I know that once I'm in this altitude, my orbit period is not going to change. I'm going to revisit this particular spot on the Earth again. This allows me to just kind of like, oh, I expect every 4.3 days, every 3.8 days, every 7.9 days, my satellite will pass by at exactly this azimuth, this altitude, and this elevation. So it's a very useful orbit design tool. And this was the focus of our research in early 2020 or 2021. And so in this image right now, this is TerraSat X. TerraSat X is a SAR satellite, which my PhD advisor used to work on when he was like my age 20 years ago. This is Tandem X. Tandem X is a direct duplicate. It's a replica of TerraSat X. And basically it's an interferometric SAR mission. So for interferometry, where you want to make sure that you get all that constructive, destructive interference exactly at the points where you want it, the distances between your satellites flying in formation have to be very, very precise. And so not just the relative position, but the absolute position too, because you want to see the same place from the same viewing angle. So we want to make sure we create a trajectory that kind of repeats itself. And it kind of looks like this, right? So let's say I have a single satellite that just moves along in a single trajectory. And this is the ground track for one orbit. Can I then select the initial design parameters such that for the rest of the orbital trajectories, it just kind of follows the same path again and again and again. So this precludes drag. This doesn't include drag. This doesn't include perturbations, which mandates that we need to do orbit maintenance for that. So this is the repeat ground track part of it. And the frozen orbit part of it is, right, because you want to, we have a question. Okay, we have 2 questions. Let me try to spend like just 1 minute on it each. How likely are small satellites subjected to experience perturbation effects when in orbit? So most small satellites are in low Earth orbit, because for a geostationary orbit, typically most satellites need a much bigger fuel tank to get there, or at least to just kind of stay in their parking spot in geo. Right? For small satellites, the biggest perturbing effect is probably drag, especially if you have a large area object, for example, a large antenna, large solar panels. It's not about likelihood, it's more like how drastic is the effect. So I actually have an open source app on my GitHub. It's called Orbit Maintenance and Propulsion Sizing Tool, that you can use to just kind of see how your orbit decays over time, given some area to mass ratio. Second question, if we have our desired targeting orbit incline angle 45 degrees and we suddenly have to change the incline angle to 60 degrees for some urgent condition, what would be the best method to change suddenly between the angles? So this is a bit of an advanced research topic. If you were to if this was like a consultative question, then I would say that if you are, for lack of better time, then you have no choice but to perform a maneuver that is in the direction of the relative velocity difference between a 45 degree and a 60 degree, and just point it that way and you just do the maneuver. If you have time, right? If like your mission is like 6 years, it's designed to last, then you can bring it up to different altitudes, just let it wait, let the inclination slowly precess, for example. So for example, the Earth's bulginess actually makes it such that a 2-body satellite orbit is no longer a constant, right? The satellite is just kind of like, the orbit is just kind of like wobbling around. the RAN is precessing, the inclination precesses a little bit. So you can actually exploit some of this if like you have time, but it takes a really, really long time for your orbit parameters to just like precess a little bit. So best method, it really depends on your metric, right? If you're measuring it based on time, if you're measuring it based on money, or if you don't have time, but you have a lot of fuel, then you should just go ahead and do a propulsion maneuver. Thamir asked, can you give us some examples of frozen orbits? Yes, so frozen orbits, so there's two parts to it. So some of the more recent design work, so 10 years ago, TerraSat X was, more than 10 years, 16 years ago, TerraSat X was conceived, and 10 years ago, TerraSat X concluded its successful mission. It is still flying today. We are still getting data from it. Even we flies in a polar orbit. So a repeat ground track orbit is an orbit such that you select the initial conditions for the 6 orbit elements such that the ground track is repeated. But often case that is not enough, right? We don't just want it to follow the same XY. So if you look at this 2D plot, it's kind of like an XY plane. We want in the Z direction, in the Z axis also, we want to make sure that the satellite's vertical altitude doesn't vary too much. And this variation happens because remember, let's go back to argument of perigee, right? When precession happens, what happens is that in reality, there's no such thing as a purely circular orbit. It just doesn't happen, right? Because the Earth is not a perfect sphere. There are perturbations everywhere. The argument of perigee is the argument where the highest point is, and this guy precesses over time. This also means that for an observer on the Earth, the satellite kind of oscillates between its minimum possible local height and the maximum possible local height. And what you want to do is you want to see if there's a way to find the optimal set of initial conditions that minimizes this. So this was a topic of it was quite an interesting topic because it was researched into in the 70s, and then in the 80s for the European remote sensing satellite 1 and 2, and then again for TerraSat X, and after that there wasn't much research into it. So we decided to open up this problem again where the repeat part was there was sufficient research into how to establish a repeat ground track. There was sufficient evidence, or there was sufficient research work into how to make it a frozen orbit, but how do we actually bring them together? How do we make an orbit seamlessly repeat and frozen, right? Okay. Let's see, I have a question from, Akhil. Akhil, you have a question?
Yeah, am I audible?
I can't really hear you, Akhil.
Hello, am I audible?
Akhil?
Hello, am I audible? Hello?
Yeah, I can't really seem to hear you. Why not take it on the chat, and I will try to address it at the end of this talk, okay? Just put it on the chat. So in our research earlier this year, we talked about what are the 2 critical steps to achieve a frozen. So repeat ground track orbit refers to, again, you just want to make sure that you just want to repeat the same trajectory that you did after an indefinite amount of time on the XY plane on this 2D map. And the frozen part refers to how do you actually minimize your vertical oscillations. So we looked at an optimization procedure for this. And again, although we always say that the 6 orbit elements are very basic, they're very simple, but actually what we were optimizing were the 6 orbit elements. In particular, they were the initial orbit elements that we chose when you are launching and inserting what are the initial orbit elements that you have picked, right? And is there a very specific set of initial elements where it minimizes the variations in your latitude, longitude movement, as well as your altitude movement? So there's an optimization. So let's see what happens. So let's see why this is an interesting problem, right? This particular semi-major axis that we've picked for our orbit is about 6,570 kilometers. But if let's say I launched 2 kilometers higher, let's say I launched 2 kilometers with 2 kilometers of error, right? Then my ground track starts to look like this. So this is not a bolded ground track. This is a bunch of ground tracks being lumped together. And it looks like small, it looks tiny, but yeah, imagine the circumference of the Earth is actually about 40,075 kilometers. So even like a minor deviation away would mean that a satellite would show up 5 kilometers in the next away from you in the next revisit, or 10 kilometers away from you in the next revisit, and you may not actually be able to pick it up. So all I did, so let's look at the A value here is 6570, and all I did was change the A value to 6572, and this is just for illustration to show you what happens to the repeat ground track if a non-optimal semi-major axis was chosen. And if I actually introduce a 10-kilometer error, then I get something that's not really intelligible anymore. It just kind of flies around all over the place. It probably still has a revisit period, but just not very, not as precise and not as predictable as I would want it to be. So we've done some preliminary orbit designs that we've done. So this has already been in literature for about 40 over years. People have done this for the earlier satellite missions. And so this is just to kind of give you a view of all the possible repeat ground track solutions that we have plotted in our research for each possible altitude, right? So each point here, both graphs actually mean the same thing. I think they are actually, they might be the same graphs by accident. So the number of days on the y-axis refers to the number of days where a satellite starts at a particular lat long, it goes with this bunch of sine waves, and eventually after this number of days appears again at this exact same spot. This is the y-axis, and the x-axis is the mean altitude that we have selected to achieve this. So this is just kind of an optimization. No, it's not. This is just a search, local search space for all the possible repeat ground track trajectories. And you see it forms this very nice pattern. I always like to think that nature has very nice patterns for us to discover. Nature is always very beautiful. There's always patterns to recognize, to discover, to make links and connections. And we see this really, really beautiful plot over here. So these are basically, this chart basically means that if, let's say, I selected, I'm just going to annotate here. Let's say I selected a 600 kilometer altitude initial launch for a circular orbit at 97.44 degrees inclination, I would expect it to follow a ground track that repeats every close to like 6 days or so, right? Every 6 days, it would just follow a trajectory and it will eventually repeat back at the original point every 6 days. So this is kind of an interesting experiment that we could do. But that's the repeat part. We haven't actually talked about the frozen part yet. We want to talk about how do we actually make sure the orbit stays, it doesn't like precess so much over time. And we can actually, let me erase this annotation. This annotation is still in the way. And so we actually framed an optimization problem, which is not new. This has been done before in literature, on how do we minimize variation. So this is passive stability. We're not doing any propulsion. We're not doing any rocket thrusters. We're just saying, okay, what is the best initial starting point to be in so that I don't have to, I'll be like in my most stable state, right? And we've done some simulations on phase space variations in the eccentricity vector. For those of you who are well versed in what this is all about, in phase space variations. Phase space variations are basically just the variations of the eccentricity vector. And the eccentricity vector is basically a vector where it takes your argument of periapsis as the argument, right? So you think about polar coordinates, there's a magnitude and there's a direction. The direction is an angular direction. Then your radial magnitude is given by your eccentricity. So if you look at how much this circle varies, right? Let me annotate again. How much this circle varies, the radius of which this circle varies, gives you a measurement of how much your satellite is oscillating. So this is kind of like, it doesn't actually wobble like that. Actually what it does is because the orbit precesses. So from a viewpoint of an observer on Earth, the altitude is just kind of going up and down, because I'm just oscillating between my max and minima, max and minima. So we can pick initial conditions where we've completely minimized the phase space variations, which is still not new, but the only new and the primarily new thing that we've done is to just kind of merge these two concepts together, and also to create a trajectory filter that bridges these space errors. So if we don't do the space errors, if we don't do the trajectory filters, even after optimization, right, we compared space errors between two ground track repeats. So two full periods. Let's say I repeat one period. Okay, I'm done. Like I've finished like 6 days of my repeat. So now let's compare 0 to 6 days and 6 to 12 days, and I compare the space errors in between. And we've done it for near equatorial and a polar orbit, and we've seen that after optimization, the mean error is really, really small. It's like, what is this? This is what, 1.2 centimeters in radial axis and about 23 centimeters of mean for the polar orbit, with a standard deviation of about 100 over meters near equatorial and about 30 meters in the polar orbit. But this is still undesirable, right? Because in a control solution, if let's say we're actually flying a satellite, we want to make sure that it follows the trajectory without like sudden breakage. We don't want to have space errors. So this is the graphical evolution of the space errors that comes from this table. So this table talks about the mean space error in phase between two same reference trajectories propagated at different times. And this is the space error evolution, right? So two consecutive FRO reference trajectories, and we looked at how the space errors change. So for near equatorial orbit, we can see that the reference trajectory without drag oscillates around plus minus 150 degrees, has this nice like spinning shape. Yeah, I told you nature always has a way of making some beautiful patterns for us to just kind of sit back and appreciate. And we've done the same for a polar orbit too. And notice that the polar orbit's standard deviation is around 40 meters, which is actually really, really good. And we did a study on on these optimization routines and how we can put them together. And after doing the optimization, we did a orbit filtering technique that actually bridges this together into a continuous trajectory. So there is no deviation over time. So this was just published 2 months ago. So yeah, designing a reference trajectory for frozen repeat near equatorial low Earth orbits. So this was something new, this was something fun that we just initiated. Like, there was no funding for this, we just did this because it was fun, just try to write this out. And we managed to get it published in the Journal of Spacecraft and Rockets. That was very nice. We worked with Star Trek Initiative. So Yongjin is my second co-author. Star Trek Initiative is the... I need to drink a bit. Star Trek, they are the Korean guys who do really cool space missions. They are like DSO, but for Korea. They were a spin-off from KAIST, and they built like a lot of the satellites for South Korea. This is really, really cool. So I worked with a friend I knew on this paper. Yeah, we managed to get it published, which was nice. And so that was for single satellite trajectories, right? We can use some of these orbit design methodologies, just these 6 elements. What can we play with these 6 elements? We can use these 6 elements to do optimal orbit design for repeat ground tracks. And for the formation flying mission that we are involved in Singapore, we can also use these orbital elements. So formation flying is at the center of my research here in Stanford University. We have a few really, really cool projects over here. So like fly a bunch of satellites in clusters. So like fly like 4 satellites maybe in a tetrahedral shape. So we can sample the ionosphere volumetrically. So like you can just think of it as like you have 4 satellites each that make up a point on a tetrahedron, and this whole tetrahedron is just flying through the ionosphere. So you can pick up like plasma diagnostics. You can measure total electron count volumetrically instead of just a single satellite passing through, where like you can just collect samples in a single line. But like this time you're flying it as a volume. So formation flying is really cool. You can do a lot of new things with these concepts. And we are exploring a lot of new ways where we can design satellite formations. And so a lot of people would think like, oh, what's so interesting about formation flying, right? It's just satellites flying in orbit, just flying together. Just put many satellites in the same orbit. So so I'm gonna play an animation for you. Not sure, Samarth, are you able to see my screen?
Yes, it is visible.
Cool. So this is SDK. SDK is Satellite Toolkit. No, I think now they call it Systems Toolkit. And I want to show you an example of 3 satellites that are flying in formation. It doesn't look very interesting right now, right? Because just look, this is like, this is L1, L2, L3. Okay, let's play this. So it just kind of flies around, does its own thing. And that's because you're kind of viewing them from the perspective of a... okay, I think I have a question. If we have to launch a couple of satellites at the same time, we want them to follow the same line, how we'll make sure they don't get deviated away in the... So orbit maintenance is a very crucial part of research also. There's always optimal ways to prevent perturbation. So once you have a trajectory in mind, you want to make sure you stick to that trajectory, and perturbations are always just kind of pulling you away from that trajectory. So you need to design an orbit maintenance scheme to do that. I wrote a paper. In fact, actually, Orbit M, which is on my GitHub, does this, but only for atmospheric drag. So you can use that if that's useful for you. Because I always believe in sharing. Software is good. Software is knowledge. So feel free to just plagiarize. Okay, not plagiarize. Credit me, but use my software if you want, if it helps you in your research or your interests too. Okay, so back to this. So these are like some really interesting satellites, right? They're just kind of like flying around doing their own thing. If you notice, the trajectories they're flying on don't look very interesting, okay? And that's because we are observing the we're observing the orbit tracks from the inertial frame. So I'm going to pause here and I'm just going to switch. What if I did not observe these trajectories from the perspective of the inertial frame, but if I observe these trajectories from the perspective of one chief satellite? So let's say I have these 3, 2 of them are like deputies, are followers, and I have one leader and one chief. So I don't know if like the screen is very blurry, the resolution is very bad for you, but what I'm going to do is I'm going to enable a second set of coordinate axes, right? And notice this. Now this is really, really cool. Look at what's happening. So they're still following the same path, but if I were to actually trace out the same path around the leader satellite, look at this shape. This is beautiful, right? This is a relative orbit. The relative orbit can take the form of a pendulum. It can take the form of an ellipse, a mini ellipse. So it kind of looks like a little orbit around a big orbit, which is actually pretty cool, right? Because you can use this to design new missions. For example, if you want to do interferometry where you have very strict baselines, this is a very nice orbit design, right? Because you can control what the distances are. And you notice that I'm not doing any propulsion. These guys are not they're not firing thrusters. They're just doing their thing. This is like the natural state, their natural trajectory, and it's moving in such a beautiful path. And so formation flying gives you it's not intuitive if I just fly them without understanding, right? So I'm just going to cancel this out, right? It's not intuitive if I fly them as they are, like in terms of like how do they look like in their inertial frame trajectories. But it gets interesting if I plot out where they are relative to each other. So we call this the relative positions. And so the 3 crucial pillars of formation flying are always: 1 is relative navigation. How do you know where you are with respect to the chief? So the chief is the guy in the middle, or lady in the middle, gender agnosticism. And what is the other one? Control. Yeah, so control. You want to make sure you cancel out perturbing forces over time. And guidance. What is the relative astrodynamics that guides these trajectories, right? You want to make sure you understand them, you know what they are, so that if you can exploit them, you exploit them. Else, if you have perturbations to fight, then you have to compute how much fuel you need to do it. Let's see, I have a bunch of questions. Okay, I'm supposed to conclude in a couple of minutes. Okay, let me just wrap up. Yeah, so I've got like, what, 100 over, 30 over slides. Don't think I'll be able to finish them all. But basically, this is just to introduce the formation flying orbit paradigm. So you notice these 6 elements. These 6 elements are the same elements that we discussed at the start of the class. Semi-major axis, eccentricity, inclination, argument of periapsis, and right angle of ascending node, right? And we can use, again, we pick the initial elements in a sense. So we call this a decomposition into a first order Clorensky-Wiltshire equations. And we can actually describe relative orbits using relative eccentricity and inclination vectors. So this is not my work. This is my PhD advisor's work. When was this? This was 10 years ago. 10 years ago, he was working on this formulation. And how do you actually describe a relative orbit in space, right? You can describe it in all the manners of shapes. How do you decompose it? What are the parameters that it depends on? And so again, back to my GitHub, I have uploaded a software called Cluster, which is spacecraft formation flying relative orbit design in Python. If you guys are interested, you can always download it. You can run it on Anaconda or any Python IDE or idle if you want. And basically what it does is it helps you to describe your relative orbits, right? It shows you what trajectories it can follow based on the initial trajectory elements, orbit elements for the chief and the deputy. This is kind of like a fun project that I did while transiting between my job and graduate school. You can try to look it up. It's quite fun. This is what the GUI looks like. This is in dark mode, but if you don't want dark mode, I think I've disabled dark mode right now. So like right now it's in the standard Tkinter UI. You can just design and just play around with them. If you're interested, also since it's open source, you can explore the code just to get your better understanding of how to do an implementation into it. Yeah, and for the rest of these slides, we will be diving into space-flight dynamics. We'll be talking a bit about Newton's laws, but I don't think I have the time for it. Kepler's laws, radiation hazards in space, and then we wanted to talk about rocket equation. Yeah, there's a lot of things that we can talk about. Space is endless, right? Path corrections. Somebody was asking about path corrections. We were talking about perturbations. We talked about all the different perturbations. Talked about how we can do orbit transfers. So I will save that for, I don't know, maybe another time, perhaps. Yeah, I think that is all I have. I think given the time I was given.